each case, but it's the most integrated or the most central of all of the graphs. And you can reliably pick these things out based on how they appear in the graph. We can do the same thing with streets. So here's a basic sort of very abstract map of streets that are connected. Each street, rather than being connections between nodes, we treat that as a node because you can see that's, again, a convex space. That node is connected to 3 nodes here because that street is connected to 3 other streets. Each of those is connected to the streets that join it, and finally the last one there. So we can turn the graph of streets into a graph that represents each of those individual streets as a node and the links between them. And we can do the same sorts of analyses. Now, the one I showed you before with the farmhouses is the one on the left. That's essentially the depth of the closeness centrality of every node in the graph. There's another measure that we take, which is the one on the right, choice, we call it, which is also betweenness centrality in graph theory, which is the number of routes. If you go all routes, shortest paths from every point to every other point on the graph, how many pass through that particular node? That's the choice or betweenness centrality. But both of these are centrality measures. How central is a node with respect to the rest of the graph? And of course, they can tell us quite a lot about how space is used, how the density of traffic is likely to vary, and the sort of social uses that we might expect. So this is a graph of, integration for a map of London, treating all the streets just as I did. And you can see at the bottom, there's a really high correlation between pedestrian vehicle distribution and the centrality measures of each of the streets. So we can predict quite a lot about movement based on measures like this. The other measure I mentioned, choice, is maybe even clearer in terms of highlighting the sort of social uses and the amount of traffic you might see. What this does at a very high radius, you can do this at all sorts of scales, but if we take the whole graph together and we pick out how many routes are going through each of the segments, this gives us a very clear foreground versus background network. So the high choice streets are the ones in red and the low choice ones are the ones in blue. And you can see that there's a definite network of the very highly traversed main streets cutting through that is picked out very clearly in this. There's no indication other than the topology of streets to give you this. But again, this correlates very well with human movement. It also correlates with the sorts of streets that we would have in our mental map, the main streets that we use to get around the city. These are also the streets in which you'd find a lot of commercial activity versus the blue streets, which have a lot of residential. So we can see quite a lot about social patterns and natural movement based purely on the graph. Here it is at a slightly smaller scale. So we can take the radii at again, I think this is about 1 kilometer or so. And what you see here, instead of the main streets, you can start to see a kind of patchwork effect where you see bright red spots occurring in different places. Now, if you look at what these are actually the centers of what we would consider to be known neighborhoods. So the center of Stratford, the center of Camden Town, the center of Angel, Archway, and so on. These are the named neighborhoods, and these would be the central hubs of them, where you'd find the tube station, where you'd find the major shops, and so on. Again, this is purely evident in the choice measures from the graph. To take just another look, as I said, you can do this at different scales, and they pick up different things. So here's an example for another city. This is Beijing. And you can see at the 10-kilometer radius, so the large radius, this is taking into account fairly long journeys. It's taking account of large measurements across the graph. And you can see at 10 kilometers, you can see the background network in blue, and you can see the foreground network in sort of orange to green colors. But the highest value for choice here is the horizontal street that's about a third of the way up from the bottom. This indicates, I can show you a picture of it there. This is a major route through. It's the kind of place you might find train stations, major services, and so on. The kind of things that are relevant for a 10-kilometer radius. But if you look at it at a much smaller radius, 500 meters, so half a kilometer, sort of easy walk out to the shops and so on, you see something very different. And now you've got these sort of hot spots. You've got plenty of them. You've got several of them, roughly every 500 meters across, apart rather. But these are the centers of a different kind of neighborhood. The street that you saw before now is no longer the hottest. There are several points over it, but the highest choice, it's difficult to see in this because they're all kind of green to cyan, but the highest choice nearby is actually just off that main street now. It's not where it was before, it's just south of it. And this is actually the center of a local market. So wherever you find a high choice at this radius, you'd see local markets, the kind of places that people would walk, say 500 meters to buy their groceries and so on. And you find this reliably across all sorts of cities. So it tells us quite a lot about the economic activity, the social activity, and movement, and so on. We can also do it at a very large scale. So just by contrast, going way up to the largest sort of maps that we've looked at, this is the entire continent of Europe at a very, very high radius, but you see the same kind of patchwork effect here. And what you're seeing in the red spots, you might recognize them here. These are the major cities. So London is obviously picked out in red. I point to it all the time. But you see all of the major cities of Europe, typically as bright red spots. But you also see economic activity. If we look at the graphs on the left, which are probably difficult to see on the screen there, but these are correlations here between the national GDP and the choice values that you see on the map. And there's a pretty good correlation here. So it's able to predict not only where the main cities are, but it's also able to tell you something about the overall economic activity. At least in Western Europe, the correlation is very high. So it tells us something quite a lot about the social activity, the movement, and so on. And we can use these sorts of analyses, of course, in making design decisions. So one of the first that I was not quite involved with, but oversaw when I was working at Foster's back in 2000, was the redevelopment of Trafalgar Square, which was analyzed first by space syntax before they could they reconstructed it. And you can see on the right, this is exactly the sort of movement that was predicted based on the space syntax analyses. So it can tell us quite a lot and inform our design decisions quite well. Now, that is all by way of background in terms of the kind of analysis that we do of space. It's one way of looking at things, but there is also an entirely different one that I want to change tack now and talk about because it's entirely different. That was about centrality measures of the space. There is another way of looking at things, which is more about the cognitive, or at least based on the cognitive. And that's the kind of agent analysis that you can see here. So my late colleague Alistair Turner developed what he called exosomatic agents, which are visual agents. They can see the space around it, but they make their decisions not on some sort of internal mental map, not on terms of knowledge of the space more broadly, but only on terms of what they can see immediately. So the localizivist where they are now. And the rules are quite simple. They take a look. They have a field of vision, 170 degrees, which is pretty close to our own field of vision. And they can see different distances in different directions, of course, based on the isovist. And they make a choice, a random choice, but weighted by the length of the distance they can see in all directions. So if they can see much further in front of them than to the side, they're more likely to walk forward. If they can see much further to the left, they're more likely to walk to the left, and so on. They can walk anywhere. It's a random choice, but it's weighted. So they make that random choice, they reorient the agent to face that direction, walk forward 3 steps, and then repeat the process again. Now, what this does, of course, is to make repeated choices based only on what they can see. They have no memory, they have no plans for where they're going to go. But if you look at these over time, the individual paths may not look all that convincing, but if you look at them over time, you can see the distribution of the agents is very closely correlated to the distribution of people walking in real spaces. So this is an example of the Tate Gallery. I think the next slide, here's an example of streets in London. It works at all scales. It gets a little bit more complex, computationally intense to run the agents at this scale, but they do correspond very closely with human movement in the aggregate. They're just as good a predictor as the other measures I told you about before. Again, they're very simple agents, only 2 parameters, the number of steps and the angle of view. Both of these are both correlated very well with the overall effect, with actual movement, but also biologically realistic. Our own field of view is 170 degrees. So these agents, although they're simple, they replicate the basis of vision and movement pretty well. But they don't, as I said, look like plausible individuals. The paths they make, the overall distribution is correct, but the paths they make don't look like actual paths of real people. They sort of wander around and squiggle and look a bit more random. Now, that's the agent model that we've been dealing with in buildings, but there is another simpler agent model that can also be extended to city streets. And this is rather newer. This is work I've done over the past few years, but it's based on the same basic principle. So instead of, as I said, those agents look at the distance one can see in front of them, and they make a random choice based on that. Now, in a city street map where we don't have the widths and we don't have the full idea of how much space we can see in all directions. All we have are individual segments in which we're walking one direction or the other. But we can infer, based on the angle of how other street segments connect to that street segment, how long or how far in each of those possible choice directions we might be able to see as we approach the intersection. So we're likely, as we approach an intersection, to see further when we're looking straight in front of us, when the street goes off straight in front of us, than we can if the street turns to the left 90 degrees. So we can use that, the angle, as a function to approximate just how far we're likely to see in all directions and make a simpler agent model even than the ones that walked around in free space. Simpler because the connections between the segments are much clearer. We can only go, say, 3 different directions at every intersection, and we don't have to worry about the space in between. So this runs really, really quickly, as opposed to the, let's say for a map of London, where we might calculate the centrality. It might take 24 hours on my laptop to do a full calculation like that. This sort of agent model simulates the agent walk within seconds. So it's really, really fast. But what you see is that it also correlates really, really well with actual traffic. So the steps you can see at the left here, we position the agents pretty much uniformly, well, exactly uniformly, one on each segment, and then we run them over a number of steps. And the graph on the right shows the correlations with actual traffic. Over the first 20 to 25 steps in London, it turns out that it correlates very, very well, 80%, with actual observed traffic in this instance. And then it sort of stays there. It settles down to a steady state. And you can see in the bottom image there, this is the steady state of the agents. It does look a lot like those choice maps that I showed you before. This is actually how many people are likely to be walking on each of the streets. So what we've got now are 2 very different accounts of natural movement. We've got the first that is about centrality measures of space. That's traditional space syntax measurements. But we've also got this extra one now that is about agent-based modeling. Now that's a very different proposition. These 2 are very different because the one on the left, the choice measure, what that does is assumes that if everyone takes the shortest path from every point to every other point, how many are going to be passing through each of these streets? But it assumes that everyone knows what the shortest path is. It assumes that you have perfect access to the graph, the entire map, and you're able to optimize your route. The one on the right assumes none of that. It just assumes that agents are purely looking at the local isovist and have no further knowledge of the map. They have no memory, they have no goals. But these 2 still correlate very well. So that's an interesting proposition. 2 totally different ideas, one based on a perfect map, one based on local information only, do pretty much the same thing. And they both correspond with natural movement. Why is this the case? Well, this is where intelligibility comes in. So this is the topic of the presentation, and this, I think, is the really interesting part. So intelligibility is a measure that's been around for quite a long time. Here's an example from 1987, Hillier and al.'s paper, where they describe it as the degree to which the whole can be read from the parts. So as you're walking around the city, depending on where you are, they talked about it being a correlation between the number of connections on a street segment and how central it is on the graph. So if I'm on a long street with lots of connections, and that happens to be a very central street, it's telling me something about the long-range properties of the graph just based on what I can see locally. So the extent to which those correlate is the intelligibility. Now, this has been examined for all sorts of spaces, and it turns out that now it's just a property of the network, right? It has nothing to do with our own cognitive faculties. It's just about the correlation between these measures of streets, local and global. But it turns out that we expect our cities to be intelligible, and when we find low intelligibility, in this example here, there's a few streets circled, and these are council estates in London that have been identified as being particularly poor spaces for navigation and for all sorts of social reasons, but they are low in intelligibility. And this is what causes the problems, one of the things. So low intelligibility is considered not to be so good in terms of navigation and other social factors in cities. But we have these 2 very different ideas about what intelligibility is. So on one hand, it's described as our ability to understand the map, the intuition and knowledge that we build up over time. That's about how much information we have in the head. This is the cognitive side. But there's also the spatial side. The technical measures for intelligibility are those correlations between measures of the streets. It's how much the whole can be read from the parts. It's about how much information is there in the environment telling you at every point on the graph where you are. So these two different versions of intelligibility, one cognitive and one spatial, are often conflated in the literature. But I think the relationship is very important. So, as I said, the measures are properties of the environment, not properties of the agent. We're looking at how much there's a correlation between the local and the global. But the fact that the two modes of analysis that I showed you before, one based on centrality and one based on agent analysis that have no idea what the graph is, the fact that these happen to agree, they agree because the space is intelligible. It's that intelligibility, the correlation between the two, that allows both measures, in all of the analysis we've done, both to predict movement. So cities are intelligible. But that if all of the city spaces we have are intelligible, it means that we don't necessarily know what our own strategy is. Are we operating based on some sort of global knowledge of the city? We're planning our routes, we're optimizing them, we're operating on the map we have in our heads. Or are we operating on local cues? Are we opportunistic? Are we acting like those exosomatic agents? Both observations are the same in an intelligible space. So, but how do we know which one we're actually using? I think we all think that we're operating on the global, but perhaps we're actually operating on the local. So we've essentially got two hypotheses here. One is the hypothesis that we operate on internal representations. So we have a wider knowledge of the space, we plan a route and we optimize it. Now we know this is biologically plausible. We have mental maps in our head, place cells and grid cells. I've got an image at the bottom there indicating these. We know these structures exist in the brain. We know we can form a cognitive map. On the other hand, there's the exosomatic hypothesis that we don't operate on our map at all. We just make decisions based purely on what we can see from the current position. We don't need any memory. We don't need any knowledge of the network. We operate very much like those visual agents. We take a random walk. Now, these two hypotheses both will result in the same outcome in intelligible spaces, but we want to know which it is that we do. Now, I think we all think that we do the former, but we're perhaps we're a little bit like Herbert Simon's ant here, which I've just taken a little clip from Simon's Sciences of the Artificial, where he describes the path of an ant along a beach as being really complex. We look at it from the outside and we attribute the complexity to the ant. But as he says, the ant is a very simple machine, doesn't have a lot of cognitive capacity, but the twists and turns it takes are because at its scale, the grains of sand that we can barely see are giant boulders that it has to climb over. And that's the complexity of the environment that causes the complexity of the ant's path rather than its own internal complexity. So are we a little bit like that? Well, there is evidence, excuse me, to suggest that it's quite plausible we are. So this is a little bit of evidence by my colleagues, led by Hugo Spears, in which they sent both rats and humans in a VR environment through the same maze to search for a target in the middle and to see what their paths are. And then they did the same thing with AI models that are based on several different learning strategies to see the difference and the similarities between them. And it turns out some of the AI models don't work all that well, but the one at the very bottom of the left-hand diagram, you can see the human and the animal in the middle. You can see the paths that they take as heat maps. The one at the bottom, the successor representation, is pretty good at doing this, at learning the mazes and replicating the sorts of paths that both humans and animals would take, rats in this case. But so is the exosomatic agent, which you see at the top. Not in every maze, but in a lot of mazes, it actually replicates human and animal movement even better than the AI models. And there's no learning whatsoever. There's no internal representation. It's just taking those purely opportunistic isovis-based steps. So it's possible that a simple model can operate in the way that we do, give the same results. We've also taken a look at extensive data, again, with some of the same colleagues, Hugo Spears, and other colleagues who developed Sea Hero Quest, which is the game that you can see on the right, which has effectively a marine environment that people navigate through. And there's about 2 million samples of paths taken through this environment by people playing the game. So we can see what sort of choices people actually take in real space. Now, it turns out if we look at the choices they're making, we can decide whether they're taking a more axiomatic approach or they're taking an approach that is based on optimizing their paths. And if we look overall at the data, we can see that the area hypothesis toward the upper right here, upper left rather, which is the way that agents, the visual agents, move around, the actual data corresponds very closely, both to area and distance. So very much like those agents. But if we take a look also at, and incidentally, this is the case particularly for people who are not so good at navigating. So some people are better at navigating, they can operate on cognitive maps, but the people who are slightly less able to do that will take a much more axiomatic approach. But we can take a look, again, to compare the difference between the axiomatic approach and the route optimizing approach. And we find when people are making a choice between one direction and the next, where one direction is the axiomatic approach and the other one is taking the shortest path, that between 43 and 78% of choices are the random walking agent axiomatic approach, and only 21 to 55% are the shortest path. So people are slightly more likely to take routes that correspond to the simpler hypothesis. Now, of course, these are also spatially located, right? So depending on where you are in the space, there are some places you're more likely to be able to optimize your shortest path, and some places you're more likely to take the axiomatic approach, particularly prior to occlusions and unnoticed direction changes. So the space itself, we don't always make the same sorts of choices. Sometimes it seems we rely on the cognitive map and sometimes we rely on the space, but that depends on the person and it also depends on the layout of space. So space affects the strategy. So here's another little bit of work by Efrosini Charalambos a few years ago, who was looking at EEG and moments of pause as people navigate virtual environments. And you can see that the aha moments where people pause and have insights into the maps tend to occur when you cross a spatial boundary and you're given new information. You can see this very clearly both in where people move and in their EEG outputs. It also seems to be dependent on the types of overall maps we have. So in London, we've got a map that is quite organic. It's not really possible to easily form a clear mental map of the overall structure, and the axiomatic movement is really evident here. Right? People's actual movement corresponds very closely to those agent movement. New York, on the other hand, it is also very intelligible, but the actual movement observed doesn't seem to correspond with the sort of local decisions by the agents. This is possibly because of the clear grid in New York. We have another strategy. It's easy to form a cognitive map of the grid. It's easy to use that to locate ourselves and to plan routes. So it looks like in New York, we probably lean toward the axiomatic. Sorry, in London, we lean toward axiomatic, and in New York, we can lean toward this quite straightforward cognitive map. Now, in some places, these tools are actually used to frustrate people, to make spaces intentionally unintelligent, so people will do things, maybe not things that they necessarily want, but the designer wants them to do. IKEA is a really good example of this, and this is some work about 20 years ago by Alan Penn and other colleagues who were looking at the way in which the IKEA space, all IKEAs are pretty much the same in this way, but it is very unintelligible. So if we look at the top and the bottom maps here, the top is the centrality analysis, and the bottom is the agent-based simulation. Now, normally in most spaces, as I said, these would agree. If they're intelligible spaces, they would coincide with one another, but they're very different here. And the one that people actually are observed to take is the bottom one, the agent-based analysis. We move axiomatically because we can't really form the cognitive map above. So we're forced to sort of meander around through all the departments and possibly see more than we thought we wanted, and possibly likely buy more than we thought we wanted. So it works very well. But all of this, as I said, is centered on the idea of cities and whether they're actually optimized to be intelligible. So in cities, it seems that most of the cities we look at, there is this correlation between the local and the global. There is this intelligibility. Are they optimized to be this way so that they can convey information to us and allow us to navigate them? I think they are. One of the interesting things, and this is the current work that I'm telling you about, it's not quite published yet, but I'll be presenting it at the upcoming Space Syntax conference, these next two or three slides. One thing that's worth looking at, if you look at the way in which on these previous two graphs here, this is on the left, the vertical axis for each of them is the degree of correlation between the random walking agents and the choice measures, between these two local and global measures. And you can see the horizontal axis is the number of steps that agents take. Now, as I said, they very quickly converge to a sort of steady state after between 20 and 30 steps. But you can see in London that the curves go up very quickly, but these curves are all at different scales of choice. And the one that corresponds best with human movement is known to be about 4 kilometers. And you can see this is also the one that corresponds best with the choice measures. It corresponds at 4 kilometers, but also the number of steps the agents take toward that maximum correlation is about 20 to 30, which in London also corresponds to about a 4 kilometer walk. 3 or 4 kilometer walk. So at both cases, it seems there's a specific scale at which we reach the peak intelligibility. And if we look at this for all sorts of cities, we've got London, as I said. At the bottom, you can see the two graphs, one for Atlanta and one for Nicosia, which are the largest and smallest cities in the data set that I have on the next slide. This is a set of 21 cities. And if we look at the scale at which these two, local and global, actually correspond the best, we see they're generally around the same sort of radius, generally around 4 kilometers. There are some outliers here, Beijing in particular, Atlanta, both of which are bigger than the average, and both of which seem probably to be designed more for car traffic than pedestrian. So there's more work to be done here in explaining exactly what that is. But there tends to be a general kind of scale around that 4 kilometer scale for both correlations of distance of the agents and for choice measures. It seems that cities are most intelligible at this particular scale. Now, one of the things, these are all the cities, if you can see these down the left-hand column, but there are two graphs at the bottom, which are random graphs. Now, one of them doesn't have very good correlation at all. It's not intelligible, but one of them does. This random triangulated graph, in which is just a sort of Delaunay triangulation of a series of random points. And if we scale that graph such that the street segments are the length, the average length, comparable to the average length of streets in most other cities, we see something very unusual. It's a definite outlier with respect to the radius at which it becomes intelligible. Right. In this case, rather than a few kilometers, we're talking about, say, 100 to 500 meters, much, much smaller. But if we scale that up so that the scale of intelligibility is the same, what we actually get is the street network that you can see on the right. So this is very intelligible and intelligible at the same way as the streets of London. Now, it doesn't look at all like London. The streets are much, much bigger, 10 times the size, roughly. But if you look at London in terms of the foreground network versus the background network, as I said, the foreground network are those streets that are the major streets that come out highest in terms of choice and so on, the streets we normally use to do most of our traveling and would form our cognitive map of the space. We see that those correspond very, very clearly to these random networks that we have. The other streets are basically just infill. So what it suggests is that we're using this street network that is a real thing, and it's also the thing that allows us to navigate the streets. Now, again, there's more to be done on the cognitive side, but it looks to me, this is the hypothesis, that our cognitive maps are very good. They're sort of limited at the scale of our local neighborhoods. Right? They don't go much beyond a couple of kilometers, perhaps, in terms of knowing the intricacies of the street networks and being able to optimize the routes. Beyond that, we rely on something else, which is this more or less foreground network, which doesn't necessarily even have to be part of our cognitive map because the city is constructed in such a way as to make that intelligible as we move. And that's why it exists at that scale. It's also the scale of sort of the average car journey and so on. So it's very useful for getting around. Now, that's purely the street network, but as I said, there are other features to look at. So in the main streets that you'd be used to traveling along, of course, there are other cues, the width of the street, the heights of the buildings, how many trees there are, all of these other sort of much more subtle cues that we can pick up on when we actually see the architecture and the surfaces of the street weren't included in that map. But if we start to look at these, which again, this is a soon-to-be published paper with my colleague Tassos Varoudis, we looked at effectively LiDAR scans, local LiDAR scans of the surrounding area of each street segment. That forms a data set that we can start to use a bit of machine learning to see how well those classify things like those centrality measures I showed you before, or the difference between the foreground and background network. And we also see that there's a peak in correlations here. Correlations, again, are similarly high, about 85% or so, to predict the centrality measures or whether something's foreground or background network. And it looks, again, as though those peak at a particular scale as well. It's exactly that same scale of about 4 kilometers. So again, the street is, or the location and the network is becoming intelligible at this specific scale of about 3 or 4 kilometers, not just in the overall street pattern, but also in terms of these immediately accessible features of the superficial environment. So all of these things point to a very important concept, which is both a measure of space, but it's a measure of cognition. And it's tying those two things up that I think is the really exciting thing. This is just the start of that research, but I think there's a lot more to be done here that'll tell us about some very important concepts of the way that the environment is structured and our cognition of that environment is structured to work with it. Now, it's important because these things aren't obvious. So I told you before that those low intelligibility council estates before, those are not things that are immediately obvious if you just look at the street network or you look at the architecture in itself. We need computation, we need these methods to be able to analyze it because they're not superficial. This final slide here compares the Maiden Lane at Council Estate on the left with the Salk Institute. I put this slide together a few months ago when I was in California, just to show that there are superficial similarities, but we have to understand what's going on at the network level at a much deeper level to understand the things that are really relevant and important for making spaces as good as we can. And that's it for my presentation. Thank you very much.